Was magma? Magma was nothing but hot molten rock material which was present below the layer of lithosphere contained within the asthenosphere. So semic crust will be pushed against the sialic crust. Suppose this is sial and this is sima. So because of this pushing by the magma which is flowing beneath the ocean crust, this ocean crust would get pushed against the continental crust. This is nothing but the generation of compressive stress. We will start our discussion with the sea floor spreading. Now, there was an American scholar, his name was Harry Hess. He was studying the Challenger Ridge. The Challenger Ridge is the southern portion of the mid-Atlantic ridge. Ridges or mid-oceanic ridges are nothing but they are chains of mountains present over the surface of the ocean. It means these are mountains which are under the seawater. Do you understand that? So they are known as oceanic ridges. And if such ridges are present almost at the central location of the ocean, they are known as mid-oceanic ridges. Clear? So there is a mid-oceanic ridge in the Atlantic Ocean which is known as the mid-Atlantic ridge. So he was studying the southern section of that mid-Atlantic ridge which is known as the Challenger Ridge. The northern section is known as the Dolphin Ridge. And he was also trying to study the oceanic ridge which is present in the southeastern Pacific Ocean region, which is known as the Southeast Pacific Rise. So what he was doing? He was trying to study the mid-Atlantic ridge, and the Southeast Pacific ridge. Oceanic ridges are nothing but they are chain of mountains which are present over the surface of the ocean or which are under the mean sea level, or they are inundated mountains, submerged mountains. Do you understand that? So when he was studying these two ridges, Harry Hess found out something very interesting. He found out that the sea floor on both sides of this ridge or these ridges are not static, but they are slowly moving, or they are slowly moving away from each other, so giving the impression as if the sea floor is spreading apart. Do you understand that? That is known as the sea floor spreading. I am repeating myself one more time, students. Harry Hess, he was studying the mid-Atlantic ridge, the Challenger Ridge or the southern section of the mid-Atlantic ridge, and the Southeast Pacific ridge or the Southeast Pacific rise, and he discovered one thing, that the sea floor along these ridges on both the sides is not static, rather it is slowly moving. It means that the sea floor is spreading apart from each other along the mid-oceanic ridges or the other oceanic ridges like the Southeast Pacific ridge. He could not understand initially that what is the reason why the sea floor is spreading apart. But then when he made further investigations into the issue, he took the help of Sir Arthur Holmes' convective magma current and later on proved to us that why the sea floor spreads. So what did he found out? Let's have a look at it. To understand his concept, we must take the help of this simple illustration, and suppose this is the continental shelf, this is the continental slope, and this is the deep sea plain. The deep sea plain is actually part of the oceanic crust, whereas when we call this as the continental shelf and continental slope, they are actually part of the continents. That's why we are using the prefix continent. Do you understand that? So continental shelf and continental slope both are part of the continents. In fact, they are the margins of the continent which are for the time being under the sea water. In fact, both the continental shelf and the continental slope are under the sea water, and assume this to be the mean sea level. And we also know that the continental crust is made out of seal mostly. So we can very safely say that continental shelf and continental slope are made out of seal. Whereas we also know that the oceanic crust is mostly made out of sima. So the oceanic crust must be heavier and denser than the continental crust. It means the oceanic floor is denser and heavier than the continental shelf and continental slope, because they are, after all, part of the continent, the margins of the continent, which are inundated under the sea water. Do you understand this? Now, we know that at an average depth of nearly 100 kilometers from the surface of the earth, we have a heavy concentration of radioactive minerals which disintegrate, produce radiation, and such radiation increases the temperature in that region and causes the rocks to melt. And that is how the molten rock material are obtained more or less within the range of 100 to 400 kilometers depth when measured from the surface of the earth. That layer of hot molten rock material is known as the asthenosphere. This we have seen, students, in our last class. So I'm assuming that almost at this depth from the surface of the earth, and you can understand somewhere it might be more than 100, somewhere it might be less than 100. The average depth is 100 kilometers, clear? And we know that till the depth of 100 kilometers we have the solid rock layer of the earth, or the uppermost solid layer of the earth, which is known as lithosphere, clear? So this is the asthenosphere. And we know from our last class that the asthenosphere is actually the source of magma. Clear? What was magma? Magma was nothing but hot molten rock material which was present below the layer of lithosphere contained within the asthenosphere. So in the asthenosphere, you know, this hot molten rock material is present, and we know from the asthenosphere this hot molten rock material or magma rises, and such rise happens in a convective fashion. That's why it is known as convective magma current. See, air also rises convectively. That's why we call it the convective air current. So this is magma, and that's why we are calling it the convective magma current. Clear? So assume that from here the magma rises convectively either through the fissures or through the gaps that are present in the lithospheric rocks, or how the magma creates or paves a channel for itself through the lithospheric rocks by melting the areas where the magma come in contact with the lithospheric rock. Notwithstanding, whatever be the situation, let us assume one thing, that this magma is rising through the lithospheric gaps or through the channel that it has created, and it is finally appearing over the surface. And as it appears over the surface, you know, it is known as lava. And you know that this magma, hot molten rock material, as it is appearing over the surface of the oceanic crust, it comes in contact with the cold water of the oceans. Why I am saying cold water of the oceans? Because you know that the sunlight will only penetrate up to a certain depth in the ocean, and beyond that the sunlight would be either very faint or totally absent, and therefore the water would be extremely cold. And you understand that as the cold water will come in contact with the lava, the law of conduction will kick in, and thus the lava will lose heat to the water, and as it will lose heat, it would cool and solidify with time, thereby forming a volcanic or you can say a volcanic mountain or something like that. Clear? And if this happens throughout the floor, you can understand that a volcanic ridge would be created like this. If we can just see it from a three-dimensional kind of viewpoint, you can understand that with time this kind of volcanic ridge would be created. Suppose this is the continental shelf and this is the mean sea level. It means I am just highlighting it more or less in the form of a 3D kind of projection, so you can understand throughout the floor of the ocean, because of this emergence of lava and its spreading on both sides and then cooling and solidification, a chain of mountains would be formed of lava solidified matter, or a volcanic chain of mountain would be formed. If this is formed almost at the center of the ocean, we will call it the mid-oceanic ridge. Yes, in Pacific Ocean, it is formed in the southeast Pacific floor, and that's why we are calling it the Southeast Pacific Ridge. But anyhow, यहाँ आ जाओ एक बार फिर. Now look here, that you know that it is not possible for lava to emerge, like all the lava cannot emerge from this point. Do you understand that? It means some amount of lava must be rolling here like this. What do you understand by this? Imagine that there is a wall and I have a bucket, and in that bucket I have molten iron, hot molten iron. For the time being, just neglect the thought that of what material that bucket might have been made up of, but just for the sake of imagination that that bucket can hold hot molten rock material, and I have a brick wall, suppose. And this is what I do, that I pick the hot molten rock material with the help of a mug almost made out of the same material as that of the bucket, and I take that hot molten rock material and throw it against the wall. If I keep on repeating this, what would happen? You can understand that a hole would be created in the wall. So similarly, as this magma splashes at the bottom of the ocean floor, with time it creates a hole in the ocean floor, and through that hole the magma emerges, becomes lava, cools, solidifies and forms the oceanic ridges, and depending upon its location on the ocean floor, we call it mid-oceanic ridge or the southeast oceanic ridge, northwest oceanic ridge or any other oceanic ridge. Do you understand that? But go back to that experiment, you can understand that when I would be throwing the molten iron material against the brick wall, whenever the hole would be created, if I keep on repeating that even after the creation of the hole, you will understand small amount of hot molten iron material may escape out of the hole, but a greater amount may splash in and around the hole in all directions. Do you understand that? So that is what I am saying. Suppose this hole has been created and thus the hot molten rock material is rising through this hole, emerging, cooling, solidifying and turning into a ridge, but yet a large amount of it would be splashing around. Do you understand that? Splashing around in all directions. I cannot show that because this is a 2D kind of surface, so you can understand that. And if this keep on happening, you can understand that this splashing also will keep on happening underneath the sea floor. Some amount of magma would definitely keep on emerging, but a greater amount would be splashing around just beneath the hole, or around the hole rather, from where the magma is erupting. Do you understand that? Now, think of this. Suppose I have a boat like this, which is dipped in water, or it is floating on water, and this is what I do. Suppose this is a boat, and I do not touch the boat, but I move the water which is beneath the boat in this direction. It means I push the water in this direction. What would happen to the boat? Yes, the boat will also start moving in this direction. Similarly, if the magma is moving in this direction beneath the ocean floor, what would happen to the ocean floor? The ocean floor will also start moving along with the moving magma. Do you understand that? And if the magma would be moving in this direction. It means this part of the ocean floor will start moving in this direction, and this part of the ocean floor will start moving in this direction. So it would give the impression as if the ocean floor is spreading apart along this zone of volcanism, because the emergence of lava is nothing but volcanism. Do you understand that? In fact, this is known as the spreading site. Along the spreading site, what you will find the volcanic ridge, and you will find that the sea floor is slowly diverging apart. Do you understand that? So we can call it a region of also divergence. Now you see, the moment the sea floor will diverge apart, you can understand a gap would be created, and magma will take the help of that gap and will emerge out. Do you understand that? And the magma will cool, solidify, and the solid igneous rocks will fill the gap. But you understand that if it keeps on moving in this fashion, both the blocks of the oceanic crust, then you can understand this process will also keep on going more or less. It means the igneous rocks will keep on forming in the zone of volcanism or along the spreading site. And if new rocks are created, can I say that is creation of new crust? So hence, at the trailing edges, if this is moving in this direction, the oceanic crust, then this would be the trailing edge of this oceanic crust, this piece of oceanic crust. So along the trailing edges, new crust is developed. In fact, new igneous rocks are formed, and new igneous rocks means new crust is being developed. That's why this is also known as the zone of creation, because here new crust is being developed. Why the new crust is being developed? Because the sea floor is spreading, and this creates a gap which facilitates the upwelling of magma in a convective fashion, and this magma cools and turns into igneous rocks. These rocks get attached to the trailing edges of the spreading oceanic crust. Do you understand that? In that way, new crust is being formed at this region. So देखो अभी तक क्या समझा हमने? That here it is spreading because of the movement of magma beneath, and there is formation of new crust along the spreading side. That's why this is also known as the zone of creation. Do you understand that? Now look here, as it keeps on moving, and obviously it would happen in both directions, but I am just showing you one direction. As it would keep on moving, you can understand that here is where up to we have the Sial. So this is the Sial Sima boundary. This is Sial, which is the continental shelf and slope, and this is Sima, which is the ocean floor. So Simaic crust will be pushed against the Sialic crust. Suppose this is Sial and this is Sima. So because of this pushing by the magma which is flowing beneath the ocean crust, this ocean crust would get pushed against the continental crust. This is nothing but the generation of compressive stress, or the compressional stress will start occurring at this point. And you know that Sima is denser than Sial, because the oceanic crust is heavier, hence more denser than the continental crust. And you know by simple law of physics that denser things sink while lighter things rise. Like hot air rises but cold water sinks. So similarly, if the Sima is denser than Sial, you can understand that it would sink under the Sial. And therefore you can see along this Sial-Sima boundary, or along the boundary of the continental crust and oceanic crust, the oceanic crust will get destroyed. This is the zone of convergence. because here two kinds of crusts are converging against each other. This was the zone of divergence. They are going away from each other. Here they are moving towards each other, or at least one is pushing against the other. Do you understand that? That's why we are calling it as the zone of convergence. At the zone of convergence, there would be destruction of the crust. Do you understand that? Like at the zone of divergence, there was creation of new igneous rocks. At the zone of convergence, the old igneous rocks would be destroyed. Why? Because the oceanic crust subducts under the continental crust. And why is that subduction? Because the oceanic crust is denser, heavier, and heavier things sink. Do you understand that? And you can understand that this magma which is splashing around and moving beneath the ocean crust, it would keep on happening because this convection is keeping on happening. So that's why you can understand it would further continue with this subduction. The oceanic crust will continue with this subduction even at greater depth, because it is being pushed from the back by new oceanic crust which is being created at this zone, which itself is moving because of the movement of the magma beneath. I hope till now you have understood everything. Now you can understand that if this oceanic crust, it reaches approximately the depth of 100 kilometers, then it will enter into the asthenosphere. And the moment the oceanic crust enters into the asthenosphere, the temperatures there are so high that the rocks will melt, and the rocks will again become a part of the asthenosphere, or the asthenosphere is also known as the source of magma. There is another name for asthenosphere which is substratum, because it is the substrata or layer beneath the lithosphere. So you can understand that this is how it is happening. So you can see the magma which is moving more or less in the form of a conveyor belt. What is a conveyor belt? Like suppose when you collect your luggage at the airport, you see that a belt keeps on moving like this and you wait for your turn of luggage. So that is the conveyor belt. Or you think of in assembly line production in a factory, and you see there are some machines which seal the object, there are some machines which punch the object, there are some machine which package the object, there are some machine which pick the object, there are some machine which smash the object, something like that. But the object keeps on moving along a belt, and the machines are placed at different parts of the belt and they keep on working on the object. Do you understand that? That is the conveyor belt. So if you have a look at this movement of magma, it is more or less similar to that of a conveyor belt. That's why this is also known as the conveyor belt approach. Do you understand this? Now students, this is what was the seafloor spreading concept of Harry Hess. I'm repeating one more time. I'm saying that the convective magma currents are responsible for the movement of the seafloor, and the convective magma currents was the idea of how the magma currents rise. They were given to us by the scholar Sir Arthur Holmes, and Harry Hess used the ideas of Arthur Holmes and further proved to us that how the sea floor is actually spreading. Do you understand that? Along the divergent zone, new crust is being created. This is the spreading site, whereas here old crust is being destroyed, because the oldest crust must be present here and the newest would be here, because as the sea floor is spreading like this, so what was formed at the earliest time, it must be farthest from the spreading site. Do you understand that? And therefore old crust gets destroyed along the subduction zone. This subduction zone is also known as the Benioff zone. Do you understand that? And why the subduction takes place? Because of compressive stress and because the Sima is heavier than the Sial. Do you understand that? So new crust which gets created at the spreading side gets compensated by the destruction of old crust along the zone of subduction, or you can call this as the subduction zone or the Benioff zone or the destructive zone. Like this was the zone of construction or constructive zone. This is the destructive zone. Do you understand this? This finding of Harry Hess, it revolutionized a lot of literature in geography that was to follow, because now everybody understood that actually seafloor is spreading, and if the seafloor is spreading, that must be having some influence over the spread of the continents or the drifting of the continents. Remember, Runcorn's findings, paleomagnetic findings further added credence to Wegener's premise that the continents are not stationary, rather they are slowly drifting over the surface of the earth. And seafloor spreading further gave indications that Wegener is perhaps right.